And so it'll generate all these edges, but it won't kind of do them independently. This one used twice, you don't want to have to you don't want to have to traverse this edge twice. So, you know, if you remember how Dijkstra's algorithm works, is kind of is spreading out as you go through here, and it marks how many steps it took to get to each vertex. You see a new vertex if it has either it has not been seen before, or the number of hops it took to get there is smaller than before, then you replace it. Or you can do things with doing breadth first search, and then you know, as soon as you get there, it has been marked before, then you can add it in. And so it'll only go across this center edge once. So then we need to calculate how many vertices were over here that it came back across here. And so it's a little tricky. You have to you do Dijkstra, and then for each one you kind of do backtracking to accumulate the count in each of the edges. Okay, and so writing out the details is a little messy. You can start to see how it works. There's one case I want to mention that's a little tricky here. And getting this to work. Let's say that I'm doing the shortest path from this vertex. What happens is Dijkstra will go both of these ways, and then it takes 2 hops to get to this vertex and back again. So then as I'm accumulating the number of shortest paths on each edge, I can go backwards here. I can mark this one as a 1. Okay, I can mark, then when I get to this edge, there were 2 shortest paths here. There was the one that started from here going to this edge, and the one going to this vertex, and the one going to this vertex. But there are 2 ways to get to this vertex, so I actually need to split this cost. Half the time, there are 2 equally short paths getting to this one, so I half the time go here, and half the time go on the bottom part. So this edge only gets half of the weight going backwards. So this actually gets a value 1, and a value 1 up here. This gets a value 2, and then I join these together, and this gets a value 5. So starting from this vertex, this edge gets a weight 5. This one 2, 2, 1, 1, and 1. Okay, and these had 2 1/2s that were split from getting to this one and from this one. So there's some details you have to work out if you're actually calculating this. Okay, so if you do this correctly, you can get this to run in time that's number of vertices times the number of edges. And this is still pretty slow. If you're dealing with a really large graph, so if you say the Facebook graph, Facebook has over 1 billion people on Facebook now. So just the number of vertices is going to be 1 billion, right? And the number of edges is going to be larger than that, right? So over 1 billion squared steps you need to take. This is going to be way too long to do on these large social network graphs. Even something with 1 million here, 1 million squared is still way too big. So calculating between this is kind of a really cool property, and it really tells you which are the important edges here that really control these communities. But it's really slow to calculate, even with this careful algorithm where you don't have to construct all the individual shortest paths. So this is still a challenge in the community of a way of doing this at scale. So if you remember, with spectral clustering and pagering, it basically started with the very sparse matrix, where we could translate the graph into a sparse matrix and then do some form of eigenvalue calculation or eigenvector calculation. And we had a way of doing this on MapReduce. This could actually scale to these large graphs because we could keep the matrix sparse and so forth. So even though it was slow, we could do this at scale. With between this, It's not really clear how to do this at scale yet. I have not really seen this. People have tried to come up with ways to, say, approximate these values, or to, some way where you got close to this that was scalable, maybe by sampling with which vertices you ran this from, or by sampling a smaller part of the graph. And most of these, as far as I know, have been fairly ineffective, and they have not really gotten very accurate results. So this is kind of still a challenge in the community. How can you scale up this notion between us? All right, so given, but if I was given the value betweenness on every edge, how would I use this to find define communities in the graph? So what would you do there?
So remove those edges which have high betweenness, and you'll get the community.
Yeah, right. So you'd find these high betweenness edges, and you would kind of cut these out, and the parts that are left, which are connected, are going to be these on these communities in the graph. Right. So it's crazy. Once you have the betweenness, you can kind of remove them. These are the ones going in between communities. So if you remove the ones going in between, the high betweenness ones, then what's left are just going to be the communities. And things that are not really connected very well after you've removed these are probably not really interesting, are probably not very interesting parts of the graph, or kind of these communities. So if you had kind of a community here that was kind of densely connected, even if I had this, and I had a lot of, say I could get from one part of the graph to a different part of the graph going through here, but this had a lot of edges, then I would spread them out because I had multiple paths. So even if it was a kind of a hub community, it would still be much denser than these other edges on either side, which you'd have to kind of connect between the different communities. So by removing the high betweenness communities, you can identify the kind of the high betweenness edges. You can identify the core communities. Okay. So one last note on this is you can do a similar thing with vertices instead of edges. You can just count the shortest paths that go, how many times, or what fraction of shortest paths will go through a certain vertex instead of an edge. And the calculation is going to be basically the same. Then if you're doing that for vertices instead of edges, these are kind of the people who are the hubs of the social networks. They are kind of going between the different parts of the graph. All right. So any questions on this?
So this, if it's still an open problem, how can this come into define?
Well, so people use it on not too large graphs. So the other thing about these really large graphs like Facebook and Twitter and so forth is you and I who want to analyze them without working for those companies don't usually have access to the full graphs. So that they will often, a lot of these companies will put online kind of these subsets of the graph that they say are kind of representative. Or people in academics will build some crawler which will go and try and grab part of this graph and build it themselves. But they usually don't get the whole graph. It takes a lot of, it's costly actually to store these things. So if you're Facebook, you're bringing in, billions of dollars in advertising money, the storage cost is nothing for you. But if you're an independent person or a small company trying to do this, even just storing the whole graph is painful. So most people don't have access to the full graph, and they'll run this on smaller graphs and try and make conclusions about those. If you have, if you had, say, like even 10,000 vertices on the graph, and let's say like 100,000 edges, you could probably run this. So it would take a long time, but you could probably do it. So, so you could fit all that in memory, and you can do this in each vertex in parallel, and you could probably calculate. Then once you have it, you have this identification of your graph. But if you have like a million or a million or more vertices, then it's no longer going to be possible. And that's the scale at which people don't really know how to run this. All right, so the next kind of way of talking about communities we'll describe is called it's called modularity. And this kind of, maybe strangely, at least I found this kind of strange, this did not come out of sociology, this did not come out of computer science, this came out of some people working in physics. And this is trying to say, so this is given some subset of the vertices C. You can think of a cluster, or as is going to maybe be a community of the graph. You want to define this notion called modularity on this cluster. Okay? And so this is basically going to be the, or defined as the fraction of edges in C, so minus the expected number of edges in C. Okay, so I'll go and define this a bit more precisely. But the idea is that if you have an expected number of edges in C based on some model, but you have more edges between the nodes in this subset of vertices C, it's more likely to be a tighter community, right? So we're trying to kind of organize the nodes by using the edges as only measurement we have. Okay, so how to define the fraction of edges in C? So this is defined as so we'll think of representing these edges, this edge set, as in this adjacency matrix, right? Where we had this matrix before, and there's a 1 if there is an edge, and there's a 0 if there's no edge. And in this case, you could probably replace this with some continuous thing in the two. Okay, so we're going to have this adjacency matrix, and so the fraction of edges in C is going to be the sum over I and j, which is in the set C, times the value of this adjacency matrix. Right, so if I look in this entry and it's a 0, then I don't do anything to the sum. If I look in there and it's 1, then I include something to the sum. So this is going to be the number of edges in this set. But I've counted things twice, because I've summed over I and j, and so I can go in both directions. So maybe you can think of directed edges if you want to, but typically they think of this as undirected graphs, and this matrix is symmetric. So maybe it's better to actually say I and C, J and C. And so then this counts the number of edges in C, and so the fraction is going to be the number of edges, and this is divided by 2. Okay, so this is how we get the fraction of edges in here. Now I need to define what I mean by the expected number of edges. Okay, and so we're going to have, and instead of this adjacency matrix here, we're going to have defined some expected matrix. I'll call this X. Sometimes it's E, but this is our edge set. So expected matrix ij. So how would I define the expectation of having an edge between two nodes I and j? What's the right way of doing that?
Total number of edges in the graph by possible number of edges.
Well, that's so good. So this is kind of the first way. You can think of the number of edges divided by the size of the vertex set choose 2, right? So number of vertices choose 2. Right? So this is good. But this is a good guess, but it's not what is used here. This goes back to this Erdos-Renyi model of these graphs, and people have shown that this does not really capture this edge distribution. This does not follow this whole thing of this preferential attachment. In fact, there's this other structuring graph where each vertex does not usually have the same number of edges. There's usually a lot of variation among them. There are these people, like if you look on Twitter, like the account for CNN has like over 1 million followers. Whereas, I don't know, does anyone have over 100 followers on Twitter? Okay. So one person is over 100 followers, right? So there's a very wide, distribution in the number of the degree of these vertices too. So if this community includes just one vertex that has CNN, CNN in there, then it's probably going to come out pretty good here because it's going to have a lot of edges in this graph. But that's not really what you want. CNN does not form a community. This is more of kind of one of these spokes in the graph, the center of a star. That's not really a tight community structure. So you kind of want to factor in what the degree is of these graphs. Okay, so what they say instead is you want to look at the degree of these vertices and say, if you have to, so I'm going to define, I'll use delta is going to be the degree of a vertex I, right? And so this is the number of edges in the graph that have I as one of the vertices, right? So is it clear what I mean by degree? Everyone's. So if I want to use this degree in this definition. So if delta I is high, then xij is likely to be high. Okay, so I want to kind of treat these independently. So then I somehow want to multiply together delta I and delta j. And this will give me, but this is not the right number either. These numbers are both greater than 1. This should be the expected value of this edge, whether it's going to be between 0 and 1. So that essentially the probability that there's an edge between I and j. So what I want to do is to divide through each of these by 2 times the number of edges. Okay, so what this is saying is that if I look at I and j here, and there are lots of other kind of edges coming off here, there are also these other vertices which are not connected to anything. Okay, so what this is saying is that if I look at a random I and a random vertex, I'm equally likely to put each of my edges in each of these locations. And that's what this component is doing for delta I. And I'm saying the same or this was delta I, this was delta j, doing the same, and I want to kind of combine these two things together. Yes. But this isn't quite the right thing. This is the probability that any one edge is, that if I place one edge in the graph, I'm going to place it here. Okay, but I'm putting a total of this many edges in the graph total, so I multiply through by this number of edges. So that means that the probability I have one of my edges coming in here. Okay, so each of these is here. So that's saying of all the edges that are out there, delta I of them are around this vertex. And so I'm going to place it anywhere in the graph, but I'm going to more likely place it close to this vertex. So the 2 is here because each edge is associated with 2 vertices. So I need to kind of share it. So I only get to count half of these edges for myself. And so I do this for both of them, and I multiply through by e. And so that means of all the edges I place, what are the probability I place one here? And so, you know, there are other ways you could model how you place these what you think the probability in edges in one of these locations, but this was the one chosen inside this definition. So this goes, and then here I can say 1 over so then say the expected number of edges in this set is defined here, where these are only the vertices in this. I only consider the vertices in this community. So if my community is only these 3 edges, or is these 3 vertices, right? Then I consider that I'm considering I being I and J being each of these 3, and I'm saying the number of edges I saw was 3, so the fraction of edges was 3 out of E, and this is the expected number of edges was the probability of each of the edges divided by the total difference. I think I may divide through by 2 twice here. So I think so often this is defined only divided through by 1 or 2. So I may. Yeah, so I think usually this is actually defined as delta I delta J divided through by 2. So I think it's something a little wrong here, but so that way I can move this to 1 over 2e out front. So I guess I should have multiplied through by 2e because I'm placing each of these twice now. So this quantity of a community, a subset of the graph, is known as the modularity. And if you work this out, if I've defined this correctly, which I think I have now, if this C is the whole vertex set, then the fraction of edges minus the expected number of edges should be equal to 0. Okay, so if C, so the modularity of V, the entire vertex set, should equal 0. It's defined, so this is the property. It's also defined so that for any arbitrary subset C, then this value is in the range of -1/2 and 1. Okay, so it's somewhere between -1/2 and 1. And typically the rule of thumb I've heard that if QC is in say 0.3 to 0.7, then this is usually a pretty strong community. This is a large modularity score, which means you have a lot more edges than you would expect. And this is probably a good choice of community. And it's pretty rare to get above 0.7. I think you'd have to, so it's hard to do examples that aren't really small, but I think you'd probably have to put almost all the edges in this community structure and very little edges outside. And probably have some nodes with no edges on them or some weird stuff like
Will
that.
the complete graph have modulated one?
So the complete graph. So it's every, well, so one thing is every community of the same size will have the same modularity. So then, I don't know if I wonder if every community of any size that you try would have modularity 0. I think that's the case. Okay, so what would happen here? So let's say, find this. So what I need is in the complete graph for the expected, the probability of an edge to be 1. I want, if that shows up, then these are going to cancel. Okay? And it should be 0. So let's see if that's true. So then the degree of everything is going to be n minus 1. So I'm going to have n minus 1 times n minus 1. And then I'm going to divide by 2 times the number of edges. Number of edges is going to be n choose 2, which is going to be n times n minus 1 over 2. Looks like I'm a little off somehow. The 2's cancel, and n minus 1 cancel, I get n minus 1 over n. So maybe I did something a little bit wrong here, or maybe the expected number of edges is slightly less. So I'm probably, I may be off by a little bit here. It's a good question. So I would think it should be. It's possible that, so the difference is probably in here. I probably need to sum over, I probably need to be more careful in here, so I'm summing over some of the edges twice in here. Maybe this accounts for the difference. So maybe this is still okay. No. I'm not sure what's going on here. It's a good question to figure out what's going on. But this, I would think that this should cancel. But it's not seeming to do that. But so it's going to give a modularity slightly bigger than 0, if I did define it correctly. But I've read that the modularity of the full graph should be 0, and that would have been the case even here. So I'll try and look that up and post it on the discussion group or tell you on Monday. So all right, so modularity. This is defined for a community, right? So, yep.
So in the expected formula, it seems that when a node has the most number of edges, it is more possible that it will have another edge. Is this the meaning of it?
So, can you say that again?
I want to know the meaning of this delta. It means that if a node has more number of edges, it is more possible than.
So this delta is the degree of a vertex. So I'm actually using properties of the graph. So I'm saying, so I want to say the expected number of edges in some community, and say this community is the Twitter graph, and it includes CNN in it. And CNN has 1 million edges. So if this is really a community in the graph, it should have a lot of people who follow CNN. At least a lot of people who follow CNN, because so I expect there to be a lot of edges in here because it has this high degree node, right? So in this example here, delta of J is equal to 4 because there's 1, 2, 3, 4 edges, right? So if this is if this is I, and I has a ton of these edges here, right? So say delta I is equal to 1,000. You know, then I expect any community that has a lot of, that includes vertex I, it probably has a lot of people who follow I, or are friends with I, just because I has a lot of friends. So, but I don't want to penalize a community because it has an I in it, either, right? If you could have a, you know, you could have you know, if a community is, you know, it's like a church group or something, right? And one of the people in the church group in the church is very popular on you know, on Twitter, right? So it doesn't mean that that's not another community. It just means we need to properly account for the very popular people within that community. And so this definition of the expected number of edges in the community takes that into account, takes into account the distribution of the population, right? So this is not a generic measurement. This is all something that depends on the properties we're getting out of the graph that were given to us, right? So if you didn't know anything about the graph and anything about the structure at all, then the best thing you can do is just to assume this Erdos-Renyi model and assume that each of the edges is distributed uniformly among everyone. And so you could also use that model, right? And so I've seen other papers that don't use modularity that's, you know, as defined as this, where they say the expectation is even across all edges. This is the Erdos-Renyi model. This is the fraction of edges that are actually there. And they use this value instead. But then you're going to be biased towards these really high degree events. So that makes sense? Okay, so this modularity tells you if you're given a community, how kind of dense are the edges in there, and it scores them. But it doesn't tell you how to find this community in here either, right? So again, between us was some property that we wanted to calculate, but we had to come up with the algorithm to do that. This is a much harder problem. The betweenness was you could write down, you could use Dijkstra's algorithm, and you could calculate it in some reasonable amount of time. You know, you want to find these communities with these high, high modularities in them. And so often the problem is actually posed as to is to find a partition of V where you have, you know, community 1 up to some community K, where each CI is a subset of V, and CI intersect Cj is equal to the empty set for I not equal to j, right? So this is some partition of all the vertices, and then you want to so you want to find this P such that the modularity of P, which is going to be the sum over I of the modularity of CIs. So you want to find this so that this is as large as possible. So you want to find this partition into these communities. And so you can pose it like this, and now this is an optimization problem you can solve. Or you can just say, I just want to find one community that has a really large score for modularity. So this is a hard combinatorial optimization problem. There are lots of local minimums in here. You can get some subset of the vertices where adding any one vertex is not going to improve the score, but there are lots of ways you can add two vertices which improve the score. So it's hard to kind of find these high modularity clusters. So typically what people do to try and do this is they'll start with a different clustering algorithm of the graphs, such as they'll do spectral clustering, and they'll break it down, and they'll start with those, and then they'll do some sort of local search to try and improve it. But as I said, the local search is not even very easy. So one kind of way, just to give you an example of this, one way you can do local search is to find all V and V, so all vertices which are not already in this community, such that that if added, that the modularity of C union V is larger than the modularity of C by itself. Okay, so you can find all these set of vertices, and maybe then you say, I'm always going to add the vertex that increases this the most until it stops. So I can do two approaches here. Add one by one greedily, the one that increases it the most, or I can add all vertices which individually increase. Okay, and so if you do this technique where you add the one by one, the one that increases it the most, this one tends to get stuck in local optimum really quickly, and you won't get very far. Where this one is not even guaranteed to improve the overall score, so you need to actually recompute it once you've added all these and check to actually get something. But if you do that, it tends to find much better, it searches the space much better. And this is only a small example of the different ways you can try and search the space. It's a very hard combinatorial opposition.
But say if you are adding one vertex which increases the modularity, then it might decrease the modularity of the other community, right?
Yeah, it's possible. So this is only finding a single community. But you could also do the same thing where this was measured over the entire partition, and you're swapping one vertex from one to another. So you could say, I can compute the value associated with the vertex by trying swapping and recomputing it. And you can actually update this in constant time if you're careful about it. And then you can get a swap score for every vertex, and either change all of them, or you can change them one by one, and try and search the space to optimize.